Okay, so welcome back to another video. Here's a little improper integral, and we have that the integrand is e to the power negative a times x divided by e to the power negative x, and then subtract 1 dx. And we also have that the condition must be that a has to be strictly greater than 1. So actually the value of this improper integral, well, it's not necessarily a value, but it's more of a product of a representation of two special functions. What those special functions are, then you will see at the end of this video. And that's where the condition with a greater than 1 comes into play as we get to that. So this is pretty much more of a easy integral to evaluate, as it's relying more along the lines of u substitution, but also that also gives us the property that we can actually write it in a way that actually give out those special functions that forms that product together. So nothing more to that, so let's actually just jump right in. As we see that if we suppose we let u equals e to the negative x, then we can see that du, differentiate both sides, is du is equal to negative e to the power negative x and dx. But we have that we need to put in dx by itself, which we can't do over here, but that's okay because I could just divide e to the negative x to both sides, and we said that that's equal to u, so we'll have that negative du divided by u is equal to dx. And so from here, we can actually now perform our little substitution, and we have to write in our new bounds. So we have that infinity for x, then that would have to mean this is going to be 0 as the upper bound. And then we have negative infinity, that's going to be infinity for the lower bound. Then if we just plug in everything back in, so we have e, then e to the negative x, so that will replace that with u, so it'll be u to the power a, and then all this being divided by e to the power u, subtract 1. Then we put in our new dx differential, so negative du divided by u. Then we can actually simplify this a little further. For 1, we have that we need to switch the bounds, so that'll become negative, and then that negative will cancel each other out. And so we can actually, because there's a base of u and u, I'll put this back over here, so that means there's going to be a -1 on that exponent. So overall, so far we have 0 to infinity, u to the power a subtract 1, then divided by e to the u minus 1, then du. Now, how do we actually take this up further and to, how do we proceed forward? In other words, I should have said it like that. Well, here's a little trick what we can do. We're actually going to multiply a 1. In other words, what term can we use to say like multiply and divide into the numerator and denominator? We're actually going to multiply a e to the negative u to, both of the fractions, so numerator and denominator. So let me, and I'll move that u to the power a minus 1 back outside, so it's not part of the fraction itself. So we have 0, infinity, then u to the power a subtract 1. So if I multiply e to the negative u to the top, so that stays like this, and then we do that to the bottom, so this will become a 1, and then we subtract this with e to the negative u, then du. Interestingly, there's something that you might be able to see, but if not, I will have to explain this anyway. But this is actually in the form of a geometric series over here. And what does that come down to? Well, let me put that note to the side and say that e to the negative u divided by 1 minus e to the negative u, it's actually going to equal this infinite sum from n is equal to 1. Yeah, it has to be 1. Otherwise, if it's 0, then that means that numerator will be, the numerator of this will be 1, but that's not the case. So this will be e to the power negative n times u. And this also is fine because we're integrating this from 0 to infinity, and then that fits in with that ratio being that it has to be strictly less than 1. So that's great. And it also falls with that absolute convergence that I can actually put that outside of our integral. So to take things, so I'll slow it down a bit. So from 0 to infinity of u to the power a minus 1, then multiply by these the substitution of that infinite sum over here. So this will be e to the negative n times u, then du. We can simply even further move that outside, as mentioned, through convergence, that the summation symbol can come out. And so we have the infinite sum from n is equal 1. And then all the way to, so actually this is going to be the integral from 0 to infinity of u to the power a subtract 1 multiplied by e to the negative n times u du. And so from here, we can now actually perform yet another new u sub. So I'll put this as let t equals n times u I have to solve this out because we have to put things in back for u, so that means u is equal to, let me see, this is t divided by n. And so if I do the differentiation, that means dt is equal to n times du. Then now if we want the du by itself, to do that substitution, that means we have that dt divided by n is equal to du. Okay, so from here, let's actually move on to another marker and finish the rest of this work, because there's actually not that much left, because that eventually that gets us to the representation of the functions we want. So we actually put this back as our new substitution. So here we have the infinite sum, n is equal 1, then we have our integral. So as we see that nothing changes from the bounds, but even if you were to put 0 infinity back, so that's totally fine. Then if we put in back the t divided by n back in terms of u, so we have now this is going to be t to the power a subtract 1 divided by n to the power a subtract 1. Put in, so e to negative nu, so that means this is going to be e to the negative t. Put in our new du substitution, which is dt divided by n. Then n can follow over here for this base, so that the negative 1 disappears, and because it's a constant, we can actually just put that outside of our integral. So that's associated with the sum. So we have 1 divided by n to the power a, then multiplied with the integral from 0 to infinity of t to the power a minus 1, and then multiplied by e to the negative t, then dt. Interestingly, we see that this function, as you can tell, this is actually a representation of a gamma function. And then over here, this is the representation of a Riemann zeta function at a. And it has to make sense to say that that's where this condition comes in with a strictly greater than 1, because if we put 1 back into here, we actually have a harmonic series, which is a divergent series. So anything with 2 or higher, of course, if you put 2 for a, that's the Basel's problem. Put in 3, Apéry's constant, and then so on and so forth. It just can't be 1, in other words. And so in other words, we can actually now replace this with the Riemann zeta of a, and then multiply by over here, that's the gamma function at a. And so therefore, there is our representation of this improper integral listed above as our given. So just like that, we are actually done with this proof. So there we have it. Yeah, that's pretty cool if you ask me.